And then we've got the fiber core, the actual glass itself. And in this one, with an orange exterior, he's going to be a multi-mode, and he's going to be rated at 62.5. So this core diameter would be 62.5 microns. If he was aqua blue, it would be a 50 micron core. If he was single mode, he'd be 9 micron, really tiny. Just your eyes. Let's go into loose tubes. Any questions so far? We're good? Good. All right. So now we're in our loose tube. In our loose tube, this is just an example. You can see loose tube fiber, depending on how big your strand count is, that are massive. I mean, we're talking, 200 buffer tubes full of fiber, each one full of 12 fibers. This is just an example that has 4. Okay, the one that Gergana brought in for me only has 2 buffer tubes in him, but he's designed the outside diameter of this cable is that they don't specialize. If you order a 24 count, they're not going to make a special outside diameter cable just because you have a 24 count. They're going to have the outside diameter made for a 48 count, so it could contain 4 of these buffer tubes. Where the other buffer tubes would be, they just put plastic members to hold the space, just so they don't have to keep remaking the outside. It would be crazy expensive if they had to do that. So these could be colored, or they could be just solid white. And if they're solid white, it just means they're a placeholder. And we'll cut up in the other end of this guy so you can see what it looks like. The central member, this is actually a piece of fiberglass rod that's used to tie off, hold, and add more strength, and also prevent you from over bending the fiber itself and shattering it. But more to that to come. So we've got the outer jacket of this guy, and unlike these other ones, we don't have a color code to tell us what the heck's going on. So we have to depend on the label that goes on the outside of the cable. And this will tell you how many fibers, what flavor he is. If it's a hybrid, it could have single mode and multi-mode at the same time. And it will tell you, here's what I got, here's where to find it, so you know what you're looking at from the outside of the cable. We have an overall strength member. In this one, it's just a foil wrap. He's pretty tough. In an armored cable installation, he would actually be the flex conduit. The flex armored metal conduit would live right there. And then we have the individual buffer tubes themselves. Central strength member, like I said, is a giant fiberglass rod. It's very similar to what we use to the push rods that we use in the ceilings. Very similar. Then we have ripcord. There's usually 2, and a ripcord is impregnated in this guy between the outside armor and the outside itself, and this just assists you getting into the fiber itself, because getting through this outside thing is tough. So use the ripcord. It'll help split open the outside jacket, and then you can actually access the fibers within. Let's take a closer look at the loose tube himself. And he's very similar to the other one. You got the buffer tube itself, and in the buffer tube versions, the colors of the buffer tube are going to indicate what number range the fibers within are, and I got more coming on that one. So just so you know, so when you see a blue and an orange here, it's just designating these are the first 12, these are the next 12. And like I said, I'll get more into him. Most of the time for OSP, the buffer tube itself is filled with a gel, a really annoying gel. The chief job of the gel is to keep moisture out and also protect the fibers themselves from hitting each other when you're moving them around. Just get something in there to keep them from hitting each other and breaking and shattering and annoying the installer. Because when you get these guys out, they're covered in goop, and you have to clean just to be able to work. All right, now we're getting to the fibers themselves, and if you'll notice right here on this one, the thing missing is that 900 micron buffer. We're going straight into the 250 coating. There's no buffer. Then we have our 150 micron cladding, just like the buffer tube. And then we have our fiber core, again, just like the buffer tube. Again, the thing missing here is that 900 micron buffer to protect the fiber itself. Whenever you are installing from loose tube, you will typically use a fan-out kit, which is this guy, and all he is a collection of 900 micron buffers. And you will feed every fiber into the fan-out kit, and that adds a layer of protection on the outside of them. You do this anytime the fiber can be exposed or needs to be handled post-installation. If you're ever using like a splice case where Once you've got it spliced away and tucked away, no one's going to touch it. You don't have to worry about a fan. There's no point. All right. Of course, I'm going to add some bonus facts. It's me. You know, people actually don't swallow 8 spiders a year. This is a popularly held belief that's just not true. It started in 1983 by Lisa Holst, who wrote an article where she made up facts just to see how gullible people would be. Unfortunately, she was really good at it, and people still think that you can swallow 8 spiders a year in your sleep. It's just not true. Everything you know is wrong. All right, so what are the advantages to using fiber, right? We've got broad bandwidth, something we're absolutely not capable of doing with copper. Not in its current configurations. Copper loses too much signal over time. It has to be re-amplified. Copper has its drawbacks. Electromagnetic interference protection. EMI has absolutely zero effect on light. Light will continue all day long, all day strong. Doesn't care how much magnetic interference comes in, whether it's a light, whether it's whatever it is. In fact, MRI machines use fiber to carry power over the machine. So they're using, it's a very ineffective way to do it. But they use light on one side, high strength light on one side, the fiber carries, and it uses a photovoltaic cells on the other side, because that is not affected by the EMI machine. The magnetics that come from the MRI machine just don't affect it. This is one of the solutions that they found to deal with it. It's kind of ingenious, but anyway, bonus info. There's low attenuation over long distances. So you can do extremely long distance runs where, again, copper has built-in resistance. Just by the material we use, it's resisting the energy we're trying to transmit down the line. So where we have a 300 feet cap on any copper run, fiber, depending on what flavor, you can kill that guy 5 times over. You can do a 5K run with fiber without even having an intermediary without issue. There's no effects from electricity, so it can be run extremely close to high voltage power without any issues to signal. It's relatively safe. The thing to remember here, especially the way that we've been observing how these guys are putting fiber in, if you use armored fiber in a building, you have to treat the armor itself as being a conductive material. You ground both sides. Bond, bond, bond. And these guys aren't doing it. So, and the case in point there is, if we've got an armor run from one end of the building to the other, they're doing some power work on one of these AC units, and they go to lunch, and that armor comes down and hits a line. It is now energized. You grab either end, you're lit up. You bond it. That way it trips the breaker immediately. That's a safety issue, so be aware when you see that happening. Say something to somebody. All right, fiber is also comparatively cheaper than copper, especially for long runs. The only real expense with fiber is the endpoints. What method are you using to inject light and receive light? But for the most part, fiber is far cheaper, especially on long runs when you have to put amplifiers and things in play. It's far more secure. It's almost impossible to tap a light source like this without someone noticing. So it's used exclusively in TS locations and SCI locations. It's very effective at keeping out people that don't need to be in.
How would you tap into it?
If you do enough of a bend, you can pick up a light scatter, and you can put some on it, but it creates attenuation. Attenuation is anything that reduces the effectiveness of your fiber signal. So, like I said, as soon as somebody does it, whoa, something's wrong. Lights go off. Yeah, it's out. Let's get into the numbering. Like I said, I was going to do. It's base 12 numbering. Base 12 simply means that the same 12 pattern repeats over and over and over again. Base 12. So the first 12 are numbered based on a color code, and then it will repeat for any consecutive numbers after that 12. So, case in point, just like the fiber that's in front of us, we have a blue buffer tube. We have our strands coming out. We have 12 strands. They're labeled blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, aqua. Take some time, memorize it. It will help a lot. So what this means is, because number 1 has been designated as blue, the buffer tube blue is designated as the first buffer tube. The second buffer tube would be orange. And the color repeats and the number sequence picks up where it left off. We only had an example of that. Look at that. So we start at 13 this time, and we go all the way to 24. And if we had another set, it would be a green buffer tube, exact same color pattern, but we start at 25 and go on to 36, and so on and so on and so on. Just keeps going. Rarely will you see anything past 24 doing inside plant. Just very rare. All right, and here's a little side cutaway of the loose tube versus tight buffer. So in the tight buffer situation, we have the 900 micron outer protective piece. Then we have the coating, and at this point, they become relatively similar. The thing to take away here is that on the loose tube, the coating itself is colored to the color of the fiber. In the tight buffer, the buffer is colored. After the buffer on a tight buffer situation, the color goes away. So this is how you track your fiber number in a tight buffer, and the coating is how you track fiber number in a loose tube. Then you can have the cladding, and then your cores. And this is to scale, so you can see what a multi-mode core is in comparative to a single mode core. Drastic difference. Good so far? Okay. If I'm boring you, say something. All right, so single mode, what's the real difference between single mode, multi-mode? What's happening at the core of it? So the thing to take away here, notice the receiver size in relation to the diameter of the core. So your light source on the single mode is almost identical to the core size. Your light source on the multi-mode extends way beyond. So when single mode is fired, it will never go past this, and it's custom tailored to ride the strand from end to end. It's very, very efficient, extremely efficient. The thing is, though, at 9 microns, the only thing that you can effectively get to emit at the modality you need to shoot down that micron is a laser. Expensive. Single mode goes up in price, but highly effective, can go a long, long, long way. Multi-mode, not so much. It's chaos. The light source for multi-mode is typically an LED, which is hard to replicate modality since multi-mode. So as he's turning off and on, sometimes the angle's hard, sometimes it's not as sharp, sometimes he's direct through. It's just more chaotic. So you're limited in the multi-mode as far as your range. Single mode kills multi-mode in range every time. Also in bandwidth, single mode you can squeeze way more down that pipe and shoot than you can with multi-mode. But this is why. They're just inherently flawed. But it's cheaper. So when you're doing something local, you don't have to get a long distance. Yeah, go with the multi-mode. I mean, seriously, the light source for a single mode, you're probably looking $300-400. The same thing for a multi-mode, doing about $10.
So what would be the length, I guess?
The limitations for each one.
So I mean the length, when you say, long distance.
That's what I'm saying. So for single mode, you can do 5K, 5 kilometers without an issue. Multi-mode, I would not do more than 3,500 feet. Still significantly further than copper. So here's where we start getting into the juice. So now we're getting into backscatter. This is also what attenuation is. And attenuation is anything that reduces the level of light you have, which will reduce your distance, which will reduce your bandwidth. Attenuation occurs everywhere, but the worst spot for attenuation is at the fiber end itself. This is just a piece of the core. This is the fiber end itself, like where it's been cleaved and cut. So this is the actual end of the fiber. Light comes in, you get your signal that comes in. The problem is on the fiber end, you're going to have microscopic imperfections in the glass because nothing cuts perfect. You can never polish it completely right. It's just not going to happen. It's going to pick up dust and debris, and what that happens, the light will actually start reflecting back. Hence backscatter is coming back. Everywhere you get backscatter, you get a reduction in efficiency and length. So I say this to bring up the mechanical connections that we use right now. So mechanically spliced fiber, you can actually splice fiber using the mechanic method. The unicam pieces that we typically use to tip fiber is a version of mechanical splicing. Oh yeah,
That's not mechanical splicing.
yes, it is.
That's all.
Please argue with John.
Please argue with me.
I'm trying to think of the name.
It's mechanical.
Mechanical splicing is a little handheld splicer.
I will prove with my crude drawing that it's mechanical splicing.
Think of the other name.
So,
I'll wait till later, I'll think of it.
yeah, this is a SC connector. This is an anaerobic.
I know he's talking about.
Yeah, because it was 3 different types of
I'm gonna let you.
Yeah.
Dry and polish.
The mechanics inside this thing are exactly the same thing that's inside your mechanical splice, which makes this a mechanical splice.
If I could think of the name, John, keep
So,
going.
within our SC connector, like we have over here, we've got a factory polished ferrule, which means from the factory, this guy is preloaded with a piece of fiber that extends to the end of the ferrule, and they polish him at the factory. So there's a piece of fiber laying inside this guy already. It's pre-installed fiber. The clamp section, where the mechanical splice occurs, this is where it actually squeezes the fiber and holds it in place. This is why it's called a cam system. It's using a cam lock to hold the fiber in place. There's a gel-filled index, so as you insert the fiber, it will actually line it up with the existing fiber. There's a buffer crimp to secure the connection once the splice has been done. You have a field prep fiber that's inserted, and notice that there is a gap. Everywhere there's a gap, you have backscatter. So, fiber goes in, he's turned and clamped in place, the buffer tube is secured in place to kind of hold him in place, and this guy's considered done. So the advantages to a mechanically spliced connection, it's quick and easy. You can be set up and done in 5 minutes. There's a low initial investment. The equipment that you need to purchase for it doesn't cost anywhere near what the Fusion guy does. Speedy terminations. What are our disadvantages here? The gel filling will expire. He'll evaporate, he'll expire. Once the gel filling's expired, the connectors are completely unusable. So if you get a batch that's expired, don't use them. It's a very high loss because, again, you're going through 3 mediums there. You have 3 sources of backscatter for that one connection where you could have 1. There's a higher cost per termination. These guys cost way more than a anaerobic. And then their connections themselves are non-permanent. Because again, you're just dealing on a mechanical connection holding that guy in place. Let's move on to the anaerobics.
No.
What?
I don't want anaerobic, we don't do that anymore.
You know.
Keep going, John, you're good.
SC cutaway. This is the same type of connector, an anaerobic version, way simplified. Notice there's hardly anything going on here. So we've got our ferrule, got our buffer guide just like before, not gel filled. He's either going to be from the factory, he'll be pre-filled with an epoxy, or you'll have to apply epoxy on site.
So what are the conditions or a preference in terms of usage between the 2 different types of connectors? Are there preference based on
The type of connector itself,
yeah, based
like
on
SC versus LC,
well,
or anaerobic versus
correct.
aerobic.
Right.
We'll get into that.
Okay.
There's advantages and disadvantages to both.
But
They both essentially do the same job.
I understand, but you know, we have customers that want certain types versus the other. I mean,
Well, he
Maybe
gotta
away from
finish the
the
anaerobic first and see what the,
This is
expectable
time
process
consuming right
first
here.
before.
Yeah, we're getting into that.
okay.
So with this one, notice the fiber extends all the way through. There's no preloaded fiber at all. The end will have to be cleaved on site and then polished. This has a far less backscatter than the aerobic connection.
There's no gap.
Yeah, exactly. There's no gap. It's glass to glass with this guy. The problem is how long he takes to prep. It takes a crazy amount of time to prep. Some customers are going to want this. I want anaerobic connections.
So that
You
was
give them anaerobic
right.
connections.
So that was my question. So you know, oftentimes, and Not necessarily at the VA, because, you know, Steve Miles will say, this is what we want, right? But on the EXO side, when Verizon tells us, okay, we need this, the recommendation or the request for, you know, fiber or the type of connectors or whatever equipment that we're going to use, they would sometimes say, we want this. So, you know, Mike and Larry will have to understand, okay, what is the condition, how it's gonna be used, and then make recommendations, because, you know, we've actually have lost money by, or actually have to go back to the job and you know, charge the customer, more money for different materials, because they, stated or recommended or say, this is what we wanna use. But if we know, okay, what is gonna be usage, how it's gonna be used, you know, the conditions of the installation and the building itself, we can say, okay, because of this, we recommend this, instead of what is stated. So Mike and Larry will also have to be a consultant to Verizon and the end user customer, on some of the jobs that, you know, we've done. So it's good to understand, okay, what are the conditions?
Mm-hmm.
Why would a customer request this type versus this type, right?
Yeah.
So that's something that,
If
it's
the
good to
customer
know
knows
as
what they're
well.
talking about, they were never asked for an anaerobic connection.
Yeah.
They really won't.
They will
They
never
absolutely
ask
won't.
for that.
Can I,
They won't.
They will never ask for that.
So here, they're requesting LC or SC, not necessarily aerobic.
Yeah, that is a connection type. SC, LC, ST,
Yeah.
these are just types. They're gonna ask for what they have available to connect to.
Correct.
Beyond that, there's no difference as far as what we're concerned.
I understand all that, but
Yeah.
I'm just talking in general, right? I mean, just because not only the fiber, but also the connectors and
Yeah.
things like that, so.
This type two will take, if you mess it up, you gotta start all over.
Yeah, it's just very time consuming. So let's get into this guy. What are the advantages? Low loss. It's got a lower loss. It's got a lower cost. Those connectors cost next to nothing. So that's a huge, huge change versus the $20 per connector. These are, you know, a couple of bucks.
And sometimes that's a deciding factor for a customer. So, you know,
You
it's
just have
good,
to-
it's good for the technician to understand and sort of educate the customer as well, because, you know, for me, let's just say me, as a business owner, and, I'm trying to save costs on a project. So, if that were my number one priority, that's what I'm gonna go with,
You-
right?
You
So.
still have to account for the added
Hours.
labor.
The hours of
Well,
hours.
understand,
We're
understand,
talking-
but,
You gotta come for a piece of equipment that's going in.
right, understand.
Yeah.
But see, this is the kind of thing that we need to make sure that, you know, we advise the customer on, right? Because they don't account for, oh, if you use this, you may save a cost in the materials, but the labor's gonna cost more because it's more time consuming. So those are the kind of things that, you know,
We don't get to make that determination. They
I,
tell us.
right, I
What you're saying
understand.
about on the
But on
commercial
the
side.
commercial side, it makes a difference.
I leave down the Verizon, people that are giving us the order, there's no difference between.
They don't, and oftentimes, and that was, you know, when that happens, I mean, our guys have to go back.
So
This
they're-
is because, so as John said on the previous slides about, the other type of connectors, they were expired,
The only thing.
and that
Yeah,
goes.
you don't wanna pre-stock as
No, we
many of those
don't,
things.
no.
This is something that we need to be very diligent about when, you know, there, you know, I
That
guess
and- that
testing
and
for
eventually-
different features. Yeah,
Any of the mechanical ones will fail.
right.
It's not a question of if, it will fail. One day it will fail.
We
These
had
don't
a
fail.
instance in, VA as well, we had just if, so we had to just dispose of them and replace them.
So if somebody needs to handle them on the regular,
Yeah, so we gotta figure
Don't count on
out
it.
how to avoid that portion, because these are expensive.
Like you said, with a unit cam, you can terminate 12 of them in 30 minutes, but a
Absolutely.
unit takes like 15 minutes.
Absolutely.
Yeah.
absolutely.
Yeah.
So we've also got non-expiring connectors, even the ones that are pre-filled with epoxy. It's heat-based epoxy. You actually bake the thing, it loosens the epoxy back up, you run your fiber through, it'll harden right back up around it. They don't expire. It's more of a permanent connection. it's glued in place. That's what it is. Disadvantages, time consuming, labor intensive, and it requires chemical handling. You are dealing with epoxies, you know, you
You
can,
said they come with epoxy, some of them?
some do, some don't. If you see ones that are called hot melt,
Yeah.
hot melt means it's already preloaded. All you gotta do is put it in a little oven, it'll bake it and
Oh, that's okay.
go to town. So, and other ones require, like the ones that Andy and I had to do, just shoot the Loctite epoxy in there and get the hardening agent, and you're handling chemicals, you can get jacked up.
Then start your figure.
Do you guys wear gloves?
Yeah,
Okay.
absolutely.
Goggles?
The green ones taste like sour apple.
And safety glasses, right?
Always.
Sure.
Safeties, we gotta follow safety.
Got another bonus fact for you. So people with orange hair are called redheads and not orange heads for an absolute reason. The color orange did not exist in the English language until the mid-1500s. Up until that point, orange was just another shade of red. So that's why they're called redheads.
Wow.
Everything you think you know is wrong. All right, let's get on the fusion splicer. All right, so what's happening with the fusion splicer? Well, the fusion splicer's job is to precisely align the fiber ends together, and then uses an electrical arc to actually melt the glass to itself, which means there is no glass face at the end of this for backscatter to occur. It is the strongest and most reliable fiber connection available.
Does that one do the stress test?
Yeah, sure does. Has the least reflectance of all joining methods. Extremely low loss. Creates a record of each termination for detailed reporting. Me personally, I like that. I like that a lot because I can say, hey, we spliced all 12. Here's a report. And one of the parts of the procedure is it actually gives you an estimated loss at the time of splicing. So you actually have that in the report. Here are all the splices that we did.
Like 0.01, right?
Which is
Minimum.
we probably
Yeah.
need to use for Excel.
You can do up to 0.3 in field,
Right,
but
right.
anything over 1, just redo it. Just redo it. It doesn't take that long. Just redo it.
It tells you on the machine too.
Yeah, it gives you a little thing. Also part of the fusion splicing, it does require a splice tray and protective sleeves, because where you fuse that glass together, he is now exposed to the world. He no longer has that protective coating. So you have to put something in play, and you also have to keep something from making him overbend, because he'll crack. He'll just snap right back open. So he requires a splice tray and the protective sleeve. And the splice tray's job, which is this guy, splice tray's job is to hold all of the splices and just keep them secure. That's his job. They make much smaller ones that'll actually go in a patch panel, so you can actually do your fusion splicings in a patch panel, and it'll hold every little adapter. And the other thing we were talking about is how time-consuming all this stuff is for the anaerobic. We can order pigtails that have factory polished ends that are anaerobically done, and all they need to do is be fusion spliced into the fiber. You plug them in, you walk away. These are already tested and good. You don't waste any time polishing and all that mess on site. I've got a single mode version and a 62.5 multi-mode version up here for you guys to check out when you want, if you want.
Anaerobic, I recommend that.
Yeah, because that's the ticket. All right, so let's get into actual fusion splicing itself. Again, crude drawing, sorry. So the fusion splicing itself actually has 2 electrodes, and it will actually shoot an arc between the 2 and melt fiber. They have 2 fiber alignment fixtures that will hold the fiber in place. So when you load your fiber in, you've got your field prep fiber. You'll have locks that go in that lock the fiber in place, and then the machine is going to go into a precise alignment, because he has to get, it's a X, Y, and Z. He has to get them vertically right, he has to get them side to side right, and get them right on top of each other. It has to be a precise alignment, because again, you want those cores have to be dead on, or else you're going to go no-go. So he moves in. If we rotate to the side, he's going to get our up and down right. He's going to bring them in together, and then zap the hell out of them. So post-splicing is going to give you an inspection where you can actually look at the fiber itself. You'll see the result via a little camera. It's got a little display that'll show you the results. The displays are going to show the fiber ends as light shine through them, just like the other examples I've given that shows the core and cladding. It'll look very similar to that. Black lines white through the middle. just like this. This would be like a pre-fusion before it gets going. You'd see fiber 1 and fiber 2, and you'll actually see them line up, and then it'll go white when the arc goes, and then you'll see the post-inspection. I'm going to show you some common post-splice scenarios and what to do about them. That's the thing to know when you're in the field. All right, so you can have a fiber type mismatch. What's the problem here? Yeah, you got multi-mode versus single mode. Never gonna fly. It'll tell you, it'll alert you. Fiber type mismatch. Go back and check your stuff. Make sure you got the right pigtails. You might have grabbed the wrong one by accident or whatever. It could be any number of things going on. So we want to make sure that we're getting like type to like type. Or someone might have ordered a 50 micron and you've got a 62.5 inch tray and someone wrote something down wrong. It'll tell you. You can force it to go. Don't force it to go. Please don't. All right. Dirty fiber. That happens a lot too. Kind of a duh, but the process, and we'll do some hands-on, is you're going to strip, clean, cleave, splice. You do not clean after cleaving. Once you've cleaved, that's as clean as that fiber is going to get. Damaged fiber, I've seen this a lot too, where you actually have cracks in the fiber. Keep in mind, glass being what glass is, I had one case in particular, the shatter went back a mile. Someone drove off with the fiber in the splice tray, in the splice trailer, and someone drove off, which just exploded. So yeah, we had to go back, I think five drops and pull slack to get the thing back out to where we found there was non-break in the fiber, because it'll just shatter all the way through the glass. And like I say, notice that some crack can extend real far back. So just be patient when working with fiber. You gotta be patient. All right, so post-splicing, here's some common things that'll occur as well. This is our ideal. It'll just look like one long piece of fiber. Nominal results, 103 or less. Again, if it's 0.01, great. Ideal is 0. You should be able to get 0. I was able to get 0 in the desert. You should be able to get 0 here. All right. So, bulging fiber. Typically what that happens here is it's arcing up too soon, and it's actually pressing the fiber in as the arc hits. And if it overpresses, it'll actually melt together and create a bulge. Too much pre-splice completion. Redo the connection. If it does it again, there is and we'll do it here as well, there is a pre-test that you can run where he'll automatically calibrate its settings, so we hypothetically won't do that. And that can be affected also by altitude changes, like Kenny and I were talking about earlier. Altitude affects fusion splicing considerably because, again, we're boiling glass. The higher are you in elevation, the faster it's going to boil. So if it thinks it's at sea level and you're at 10,000 feet, it's going to do some really funky stuff. It has to know where it's at. Some fusion splicers have a GPS antenna on them so they can figure out where they are and they'll preset their altitude automatically. There's others you just have to manually configure. You have to figure out what the rough elevation is and dial it in. And usually we want to be within about 1,000 feet. This is the neck down. This will occur when you have too much arc. It's too hot. It'll actually burn out part of the cladding. He can extend all the way up in there, so neck downs are pretty easy to figure. You want to do the exact same thing. You want to go ahead and recalibrate and try them again. Arc test, redo connection. Little bubble at splice point usually means he didn't bake long enough. He didn't arc long enough. This also happens a lot when you clean the fiber after a cleave, because you're leaving alcohol residue on the fiber. When the arc hits, the alcohol residue will burn hotter than the glass. It will burn a hole right through. Again, freshly cleaved, clean as you're going to get it. Just redo the connection, you see this thing pop up. Line at the point. Sometimes you'll see a hairline, just a real hairline, and it still gives you a great read. You're probably okay. But if you see a noticeable line at the point, yeah, too low arc time. arc test, redo the connection, which is pretty much the same thing you want to do every time if you have an error like that. Do an arc test, redo your connection. It doesn't take that long to do, especially with this machine. It's a great machine. Got one more for you. The pulling bundle part was short? No. He measured 5'2" using a French imperial scale. The French imperial scale was tossed away some time ago, but he actually measured 5'6.5" using the English imperial scale, which made him actually above height for the average Frenchman at the time. So yeah, bundle part was short. Everything you think you know is wrong. All right, fusion, splicing, post-splice. What do we do after we splice? So after an ideal splice, fiber is incredibly strong laterally, which means if you pull this way, he's pretty strong. Anything off lateral, he'll snap right again because he's missing all his protection. So we have to use, there's a little strength member shrink tubes that will be put over the fibers.
Don't forget that place.
Yeah, if you forget to slide them over the fiber before you start, you'll curse a few times as you break the fiber and start over. But it's a heat shrinkable splice protective sleeve. It's got a metallic strength member that keeps it from bending, and it protects the exposed splice point and the exposed cladding, and acts like a coating. It's affixed to the strand by the heat oven, which is also attached to the splicer. And this is just a rough drawing of what it would look like. So you got a fiber housing where your fiber passes all the way through. You've got a metallic strength member, and then the actual whole thing itself is heat shrinkable. As soon as it gets to the oven, it'll just shrink right onto the fiber. So there's a few examples of proper and improper sleeve application. We're gonna go through those real quick. Kink fiber. If you see this in there, it means he wasn't kept taut when he was loaded in. He should be straight on. So they've got a kink to him. He will add attenuation. You don't want that. Unfortunately, when you get to that point, you're gonna have to start over. Snip him out, start over. Because you're not gonna be able to straighten him out. Trumpeting. So you have different size sleeves as well. Here's another one. So the oven can be set for different lengths of sleeve. If it's set for too short of a sleeve, he baked this part but didn't bake these parts, so they didn't heat shrink to the fiber. This is the one case where you can just make the correction on the splicer and just reheat him, and he'll shrink right up and get happy. So that's an easy one to fix. You have singeing, and this is the exact opposite problem. If you're using too short of a sleeve and you have them set for the long, you'll actually burn into the coating on the outside of the fiber. And you can see, you'll feel little divots at the end of them where the oven baked into the fiber. And unfortunately, redo your connection and make sure your settings are for the right length sleeve.
West Virginia facility uses fiber a lot, or?
Pretty regular.
Yeah.
What's the length of the teeth, John?
It's preset for them. They're different for each splicer.
1.5 or something?
Yeah, well, it's not even that much. It's really small, but it depends. That's more of
That
a.
one that's measured, I don't know what you got measured.
Yeah, that's more of a splicer specific setting. There's some that are like 10, which is when you need the longer sleeves. For this one, the short sleeves, all you need for this guy.
So guys, over at Vago, you guys are still using Cat 5, Cat 6? Mostly?
Yeah, you're gonna continue to use upper.
About 6 now.
All right. You can also get bubbles that will appear after use, and this is usually a sign that you got moisture present with the sleeves. Check that they're dry. Try it again. If it shows up, get rid of that batch. Don't use that batch anymore. We don't want any moisture getting locked in there with the fiber. Ideally, this is what we want to see. We want even and complete shrink to the ends. We want to see the fiber nice and taut through the middle. Tubes free of debris. No damage to the coating and cladding. That's not me. That's not me. Who's got their system unmuted?
Somebody's practicing.
Hello?
They're still on.
Anyway, so this is just a little bonus thing I wanted to add on the end of it. A common misconception is that multimode fiber is for multiplexing. It's just not true. Does anybody know what multiplexing is? Multiplexing, anybody? Muxing, demuxing? Okay, this is good knowledge to have. It's good knowledge to have. Multiplexing is the ability to inject multiple signals over one carrier. So I can have one fiber that's just shining light, and I can turn it into 8 signals. I can turn it into 16 signals, 32 signals, 128 signals, all on that one fiber without having to rerun fiber. This is when you see like phone companies, oh, we just added, we just doubled coverage. Yeah, they added a bigger multiplexer. That's what they did. So that's why they're out there having to keep pulling more and more cable. But the misconception is, oh, multiplexing, multimode, that's what it's for. No, you can multiplex single mode, multimode, doesn't matter. You can mux on copper. But let's stick to the fiber. All right, so just talking about a little bit of modality. So when we have constituted light and we hit a prism, we know that we can refract out to multiple light sources. Common knowledge, everybody with me so far? Nothing crazy? All right, did you know you could take that broken out light, and if you precisely align another prism, you can reconstitute him. You can join all those colors right back together and shoot them on down the line. And this is the basis for multiplexing. Even though the bandwidth of light we're talking about is all in a hyper red zone, this is just for example purposes. Essentially, this is what we're doing. We're breaking it out, we're reconstituting it. So if we have a chain going, right, where we start with our pure signal, we break him out, we reconstitute him, we send him down the way, we break him out again. So this is site A, site B. If I start shining red here and I break him, he's going to break over there. I can inject my digital pattern on the red and have my digital pattern over here set to break out from red. And he'll get his 1s and 0s like he needs to. And likewise, I can do the exact same thing with the blue line. I can do a completely different signal on blue. This is multiplexing at its core. The cheapest ones are CWDM, which is coarse wave division multiplexing. They'll break out a signal into 8. They'll give you 8 signal from 1 overnight. Really cheap, easy to do. The ones that the phone systems are using right now are on, I think they're on 256. Those things are crazy expensive. Crazy expensive. But again, they're not having to run new fiber out end to end. They can just put the proper breakout mechanisms in place and start interlaying more and more traffic over top of existing connections. And that's multiplexing. That's all it is. Anybody? Good? Questions? All right. Let's play with it.
You didn't do everything fiber, man.
All right,